Okay, so in the last class, am I audible to everyone? Hello? Hello?
Yes, sir, you are audible.
Okay. I have gone through the last video of the last class, and what I can see is sometimes because of this internet connection and all, the recording is not done correctly, isn't it? So
Yes, sir.
if my voice is not clear, or if there is a too much lag in the video, please stop me in between. Then I can switch on my another mobile internet or something, because this IIT network is messing up big time these days. So I have gone through that video and I could see that at some places there was a significant lag. Even voice was not clear. So please stop me in between if such situation arise. Okay.
Yes, sir.
So I'm really sorry, because when I'm on the slide, then I don't get to know whether the internet is working well or not. Because for me, it is kind of, see, I am, presenting, so I don't get to know whether that presentation is visible or audible to everyone with a, correct pace or not. So you will have to stop me in between. If IIT internet is not working, then I will switch on some other internet, but the quality of the video has to be a little bit better. And also, if it is not getting in a correct form, then probably I will switch off my video and I will only keep the presentation and the audio on. Okay, so that will save some bandwidth, isn't it? Okay, anyway, so in the last class we started looking at the uh, radiation, and as we have discussed in the last class, that unlike the conduction and convection, where the medium and the temperature difference is required for the heat transfer, in radiation we don't require a medium or a temperature difference for the heat transfer. Of course, the net rate of heat exchange, that depends on the temperature of both the bodies. So here you can clearly see there are two bodies are shown here in this particular slide, one at 500 degrees Celsius and one at 100 degrees Celsius. So both radiate the heat, and therefore even if the temperature of the second body is 100, but that also transfers heat to a body which is at the 500 degrees Celsius. So both are transferring heat to each other, but the net rate of heat exchange depends on what temperature they are having. Correct. Again, we don't require a medium in case of radiation. Again, all the details which I have talked in the last class, which I said that is commonly done in the undergraduate, maybe 11th and 12th. So I will just quickly browse through that. So the radiation is emitted in the form of electromagnetic waves, and these waves propagate at the speed of light. Again, these are characterized by wavelength and the frequency, and these are wavelength and frequency is related as c equals to nu lambda, where c is the speed of light. Again, the radiation from the body is not continuous but occurs in the form of discrete quanta, and the uh, energy is given as E equals to h nu, where h is a Planck's constant, nu is the frequency. Again, these energies emitted because of the oscillation or the transition of the electron present in the system. Okay. As we have again discussed in the last class, that the radiations are emitted with all the wavelengths from 0 to infinity, but most of these radiations concentrating at some particular location. For instance, if you look at the visible light, most of the radiations are concentrated in the visible range, and therefore the sun appears bright to us. But uh, radiations are emitted in all wavelengths. That is what it is, but predominantly it is present in the visible light range, and that is why it appears bright. Okay, the energy of the electromagnetic waves varies inversely with its wavelength. So that means that the waves which are having the shorter wavelength will have a higher energy compared to the wavelengths which are having the higher wavelength. The radiations having the higher wavelength uh, will have a lower energy. This also we have seen that the radiant incident radiation partly reflected, absorbed and transmitted, and their factors are summed up to 1. Again, there is another property which is called as emissivity, which gives how good the surface is as an emitter. Again, in case of the reflection, it could be a specular reflection where the angle of incidence and the angle of reflection is same, whereas the another type of reflection is a diffuse reflection where the reflections are taking place in all the directions. Concept of black body, we have seen black body is the ideal body which has the absorptivity equals to 1 and the emissivity equals to 1. So it absorbs all the lights which falls on it, and therefore it appears black. Again, this is used as a standard to compare all other bodies. So if you look at the real surfaces, uh, uh, if you look at the real surfaces, emits or absorb less than the black body at the same temperature. Further, the emissivity and absorptivity may vary with temperature and wavelength. So what it means is the absorptivity and the emissivity of the black body is 1, whereas that of the real bodies is less than 1. And also these are function of temperature and wavelength. Then again we said that there is another body which is between the real bodies and the black body, and that is referred as a gray body. So gray body is somewhat ideal. Somewhat ideal means its absorptivity and the emissivity is less than 1. But the interesting point to note down here is the absorptivity and the emissivity is independent of the wavelength. So that is why we are calling it as a somewhat ideal. It is not exactly same as the black body, but the absorptivity and the emissivity is independent of the wavelength, and that is why we call it as a gray body. That is again a probably a literal meaning is used here, so that is between real and the black, so that is why it is called as gray. Anyway, okay, so up to this we have done in the last class. Okay, now let us look at the Planck's law. So Planck's law uh, states that at a given temperature, a surface emits radiation of different wavelength, theoretically varying from 0 to infinity. For same range of wavelength, the surface radiates more energy as the temperature increases. So the Planck's law says the monochromatic emissive power of or a spectral emissive power EB lambda of the black body is a function of wavelength of radiation. So EB lambda is function of wavelength lambda. That is what the Planck has stated. So again, the word here is very important: spectral emissive power or a monochromatic emissive power. So this talks about only a radiation of single wavelength. So that is why this EB lambda, this is nothing but the emissive power, but there is a subscript lambda. So what it means is this corresponds to a wavelength, single wavelength. It's not, even though the radiations are having the wavelengths varying from 0 to infinity, but here we are talking about the emissive power of the radiation having a single wavelength. Okay, so that is given as by this particular relation, equation number 1. So here in this particular equation, c is the speed of light, h is a Planck's constant, kb is a Boltzmann constant. So again, this particular equation is rearranged in the form of two constants, k1 and k2. So where the values of k1 and k2 can be given as k2 is 1.4387 into 10 raised to power minus 4 micrometer Kelvin, and similar k1 is given as 3.743 into 10 raised to the power 8 watt micrometer raised to the power 4 divided by meter. Okay. So let's look at the last point and then we will look at this particular figure. So sun having the temperature which has around the temperature of 5800 Kelvin emits the radiation with the peak near visible range, therefore it appears bright. Earth emit most of the radiations near infrared region, and therefore we are not able to see light emitted from the earth. Okay, so what we are trying to see in this particular figure is, even though the radiations are emitted between the wavelength 0 to infinity, most of these wavelengths are concentrated at a particular value. So these are concentrated at a particular value, and therefore the color is appear. So in this particular case here, you can see for higher emissive power, the peak of the graph EB lambda versus lambda shifts toward the shorter wavelength. So what we are trying to say is, remember, for all the lights, for all the radiations, the radiations are varying the wavelength between 0 and infinity, but most of the radiations present, these are concentrated towards a particular wavelength, and depending on how much is the you know uh, energy emissive power is there, depending on that, the radiations are concentrated, the wavelength is the radiations are concentrated towards a particular wavelength. So for example, if you look at the sun, most of the radiations are concentrated around this particular range between zero point 0.4 to zero point 0.7, which is a visible range, and therefore you can see here, the temperature of the sun is 5800, and most of these uh, radiations are concentrating around this region, even though radiations are present in all the wavelengths, but these are concentrated mostly in this region, and therefore the color appears. Again, as the temperature is changing, so as the temperature is, if you look at in this particular figure, as the temperature is decreased, so as the temperature is decreased, based on that, the wavelengths of the all the radiations, uh, the wavelengths are distributed between 0 to infinity, but predominantly most of these radiations are concentrating at the higher value of wavelength, because you have decreased the temperature. That means the emissive power is decreased, and now because of that, most of the wavelengths are now concentrated towards the higher value of higher value of wavelength, and uh, therefore either you will see the color or you will don't see the color, depending on whether it is in visible range or not. But as the temperature decreases, that means the emissive power is decreasing. In such cases the wavelength is increasing. The wavelength is increasing. That is what is shown here. So this the wavelength corresponding to this maxima is increasing as the temperature is decreasing. That is what is shown in this particular figure. We will appreciate this particular figure later in the next slide when we will look at the Wein's law. But what I'm trying to say here is, as the temperature is decreasing, basically the concentration of the radiations towards a particular wavelength, and that particular wavelength is decreasing, that particular wavelength is increasing as the temperature is increasing. So as the temperature is decreasing, the wavelength is decreasing. Sorry, as the temperature is decreasing, the wavelength is increasing around which most of the radiations are concentrating. So here you can see, as the temperature is decreased, most of the radiations will be concentrated towards this particular peak. Similarly, as the temperature is decreased to 300 Kelvin, most of the radiations will be concentrated in this particular region, which is towards the peak. And that is what is happening in this particular figure. Okay. Is it clear? Hello? Is it
Yes,
clear?
sir.
Can we move to the next? Okay, so you will appreciate this figure, little bit more as we move to the next slide. Okay. So what this Wein's displacement law is saying, Wein's displacement law is saying that at the peak of this graph, emissive power versus wavelength, the multiplication of lambda and the t at this particular location of the maxima. So lambda max into t is constant. That is what Wein's displacement law is saying. So lambda max into t is constant, and that multiplication is equals to 2898 micrometer Kelvin. Okay, so this is what the Wein's displacement law is saying. So as temperature increases, the peak of the graph P lambda versus lambda
ऊपर से तो
shift.
पतली स्ट्रैप आना से
Hello, hello, hello.
sorry sir, that was a mistake. I was on mute.
Okay. So as the temperature is increasing, as the temperature is increasing, the peak shifts toward the left hand side of the emissive power versus lambda plot, and also the most of the radiations are concentrating near the peak. That is what we have seen in the last slide. Now in this particular slide, what we are saying that the Wein's law says that the multiplication of lambda max and t at this location of the maxima is constant. So lambda max into t is equals to 2898 micrometer Kelvin. And as the uh, that this particular thing we can prove directly from the Planck's law. So Planck's law gives us the monochromatic emissive power. So EB lambda is given as 2 pi sc square lambda raised to the power minus 5 exponential of divided by exponential of sc divided by lambda kbt minus 1. So this is expressed in terms of k1 and k2. So this can be given as k1 lambda raised to the power 5 minus 5 divided by exponential of k2 divided by lambda t minus 1. So now we are interested in finding out this location of maxima. So clearly we have to differentiate this particular equation with respect to lambda, isn't it? Because we are interested in finding out the maxima with respect to the spectral emissive power, isn't it? So dEb lambda by d lambda, that we can directly obtain by differentiating this equation with respect to lambda, and we can equate to 0. So after equating to 0, what we get is lambda max t equals to 2898 micrometer Kelvin. So we can directly prove the Wein's displacement law directly by differentiating the monochromatic emissive power, which is given by the Planck's law. Okay. So from this particular law also we can clearly say that as the temperature is increasing, my lambda max is going to decrease. My lambda max is going to decrease because the multiplication of both is 2898 micrometer Kelvin, isn't it? Now again, this can be clearly seen if you are hitting a metal. So initially the temperature is not very high. So in such cases, you can clearly see the color of the metal appears around red. If you further increase the temperature, it appears yellow. If you further increase the temperature, it appears white. So clearly as the temperature is increasing, your wavelength is decreasing, and therefore it is moving from red, yellow to white. Okay. Is it clear to everyone?
Yes
Hello.
sir.
Okay. So now so far we were only talking about the monochromatic light. We were only talking about the monochromatic radiation. That means radiation with only one wavelength. But let us look at Stephen Boltzmann law. So what Stephen Boltzmann law is saying that the total emissive power of a black body over the entire spectrum of the wavelength. Remember, in a Wein's law as well as in Planck's law, there is this subscript we are using lambda. So this is corresponding to the monochromatic radiation, isn't it? But what Stephen Boltzmann is saying, if you wanted to get the total emissive power, what we have to do is we have to integrate this particular equation which is given by a Planck's law. So that is the monochromatic emissive power. So this monochromatic emissive power given by the Planck's law has to be integrated over the entire range of wavelength between 0 to infinity. That is what is been done by the Stephan and Boltzmann. So if we integrate this, what we get is the total emissive power. So here this word is used, total emissive power. Remember, so far we were using a word monochromatic emissive power or spectral emissive power. So when we are saying monochromatic emissive power or a spectral emissive power, that is corresponding to single wavelength. Now we are talking about the integration over the wavelength varying between 0 to infinity. So if we integrate monochromatic emissive power between 0 to infinity like this, what we get is in this particular equation. So this equation is rearranged a little bit in order to substitute the variables. So here this entire thing is represented in the form of k2 by lambda t. So here in this exponential factor there is a k2 by lambda t. So this entire equation is represented in the form of k2 by lambda t, and in order to get that these are multiplied and divided here. So here you can see this k1 t raised to the power 4, k2 raised to the power 4, this entire this k1 this k2 by lambda t is multiplied here. Okay, just wait. This has lambda raised to the power -3. So -3 is cancelled from here, and lambda raised to the power -2 remaining. So that is put here. So k2 by lambda square by t, and minus sign is there. So this minus sign get cancelled with this minus sign, this lambda square and this lambda raised to the power 3. So this get cancelled out with lambda raised to the power -5 here, and k1 as it is remain as it is. This we are, since here we are dividing by t cube and here we are dividing it by t. So therefore we have to multiply it by t raised to the power 4, and in addition to that here k2 is multiplied here, so we have to divide by k2 raised to the power 3, and there is one more k2 here, so that becomes k2 raised to the power 4. So this is just a simple rearrangement of this original equation in order to make sure that we can represent this k2 by lambda t by another variable. That's it. Okay. So we can put this k2 by lambda t by another variable, let's say x, and then we can differentiate it as dx, so that becomes minus k2 by lambda square t d lambda. So as lambda is equals to 0, here the limits are varying between 0 to infinity. As lambda equals to 0, x becomes infinity, whereas when lambda is equals to infinity, x becomes 0. So this entire integral can be represented in the form of x, and the limits are also changed. So this EB is given as k1 t raised to the power 4. This is taken out as these are constant, divided by k2 raised to the power 4, and this integral becomes 0 to infinity x cube divided by e raised to the power x. So this e raised to the power exponential of k2 divided by lambda t, this becomes ex in the bracket 1 minus e raised to the power minus x. Dx. So now this integral is solved separately. So this integral is represented here. So x cube in the numerator remains as it is, and this e raised to the power x becomes e raised to minus x, and 1 upon 1 minus e raised to x is expanded in a Taylor series expansion. So that becomes 1 plus e raised to the power minus x plus e raised to the power minus 2x, and that summation goes all the way. Now this e raised to the power minus x is multiplied to this entire equation. So what we get is integral 0 to infinity x cube e raised to the power minus x plus e raised to the power minus 2x plus e raised to the power minus 3x, and that summation goes all the way. Now this particular summation can be represented in the form of this summation sign here. So we can represent this in the form of summation sign. So that becomes summation of n equals to 1 to infinity integral 0 to infinity x cube e raised to the power minus nx. Again, we can put this e raised to the power nx minus nx can be simplified by putting nx equals to y. So if we put nx equals to y, what we get is summation between 1 to infinity 1 upon n raised to the power 4 integral 0 to infinity y cube e raised to the power minus y dy. Now here in this particular case, the integral 0 to infinity y cube e raised to the power minus y dy, this integral is obtained as 3 factorial. So this 3 factorial is put here. So now this equation becomes summation of n equals to 1 to infinity 3 factorial divided by n raised to the power 4. So that becomes summation of n equals to 1 to infinity 6 by n raised to the power 4, and this summation uh, can be represented in the form of pi raised to the power 4 by 15. So this all this here, this integral is something called as a gamma function. So and also this summation of 6 raised to the power 6 divided by n raised to the power 4, this summation is all the summations are first done by Euler. So all these details you can find out in any of the mathematics book. In fact, I can give you another reference. If you start searching about this Riemann hypothesis, there you will see this gamma function as well as zeta function and this integral. Also this Euler identity, all these things you can see if you search for Riemann hypothesis. Okay, so there you will get the details of this integral as well as this summation. Okay, so I have directly written this summation here, but you can find out in standard mathematics book, as well as you can search it in a Google. You will get all this in more detail. If you don't get these directly by name, then you just search about gamma function as well as gamma function, zeta function, and Riemann hypothesis. If you search for this, you will get all these things in the internet. Okay, so let's not waste time here. So for a timing, let's assume that this is correct. Okay, so this integral x equals to 0 to infinity x cube divided by e raised to x in the bracket 1 minus e raised to power minus x dx, this is given as pi raised to the power 15. So we can put it in the original equation. So this is the original equation. So this becomes pi raised to the power 4 divided by 15 into k1 t raised to the power 4 divided by k2 raised to the power 4. So here k1 and k2, these constants we know. We can put it in this equation, and finally what we get is this pi raised to the power 4 by 15 and k1 by k2 raised to the power 4. This entire constant values are represented in the form of constant sigma. This sigma is nothing but Stefan Boltzmann constant. So this is given as 5.669 into 10 raised to the power minus 8. So what we get from this particular slide is the Stefan Boltzmann law says that the total emissive power of the black body, this black body is very important. So for all the relations which we are deriving, these are with respect to the black body. Hello?
Sir, in the last
question?
line, is the expression for the constants correct? So it should be pi to the power 4 k1 by k to the power 4.
Yes, you are right. You are right. I will correct it. This is not correct. You are absolutely correct. Let me just correct it. Okay. This should be by, isn't it? That is what you are saying?
Yes, sir. It should be pi to the power 4 and k2 should have the power in negative.
Yes. Pi to the power 4. Yes. I'll just correct it. Give me a minute. Okay. Sorry. Update. Is it correct now? Hello? Is it visible?
Yes, sir, it is correct now.
Okay. Okay, so Stephen Boltzmann constant sigma is given as pi raised to the power 4 by 15, K1 divided by K2 raised to the power 4, and that comes out to be 5.669 into 10 raised to power minus 8 watt per meter square, Kelvin raised to the power 4. Okay, so far we were only talking about the black body. We have not said anything about the real body, isn't it? So all these relations are only for the black body. Okay. Okay. Now, uh, there is another concept here in the form of fraction FB0 lambda. What it is that we will discuss in this particular slide. So the total energy emitted from the black body for a given range of the wavelength can be represented in the form of fraction FB0 lambda of the energy emitted by a black body in the wavelength range of 0 to lambda. So what this FB0 lambda is, basically whatever is the total energy emitted between the wavelength 0 and lambda divided by the total radiation emitted between 0 and infinity. So that is what is this FB0 lambda is. So that is what is calculated here. So FB0 lambda is nothing but the total emissive power, total emissive power. So total emissive power between the wavelength 0 to lambda. Remember, the total emissive power between 0 and infinity, that is divided in this particular equation. So this is calculated in the form of fraction here. So FB0 lambda is nothing but the fraction of total emissive power between the wavelength 0 and lambda divided by the emissive power between 0 and infinity. Wavelength 0 and infinity. So that the fraction is calculated here. So again, remember the total emissive power between the wavelength 0 and infinity, that already is given by sigma into T raised to the power 4. That is what we have concluded here, isn't it? So the total emissive power of a black body between the wavelength 0 and infinity is given as sigma into temperature raised to the power 4. So that is what is substituted here. So this denominator is substituted by this sigma raised to the power T raised to the power 4, and the numerator is represented here as 0 to lambda K1 lambda raised to the power 5 minus 5 divided by exponential of K2 divided by lambda T minus 1 d lambda. So this is equation number 6. And as you can clearly see, if you wanted to solve this integral, remember solving this integral for this extreme limit of 0 and infinity was still able, we were able to do it using this gamma function and this Euler summation. But when we are doing it between 0 and a particular value of lambda, that is not easy. So this integral is not easy. This integral is not easy. Okay, so that is why this fraction values with respect to lambda t, this fraction values with respect to the lambda t are in general reported in a tabular form like this. So there is a table 7.2 in the book. I have also given this table here. So as the lambda t varies, how this value FB is varying, that is given. So once you know this factor FB, you can directly calculate the factors for some other values. For example, if you are interested in finding out the FB values between the wavelength lambda 1 and lambda 2, so this can be represented as FB 0 to lambda 1 minus, sorry, FB 0 to lambda 2 minus FB 0 to lambda 1. So this first factor you can find out from this table. Similarly, you can find out the second factor from the table, and then you can subtract. So you don't have to do the complicated integral like this. Please remember, whenever the question is to calculate the fraction of the emissions between emissive power between the wavelength 0 and lambda, you don't have to solve this integral. Solving this integral is going to be extremely difficult. Instead of that, what you have to do is you have to refer a table which is given in the book as well as in this particular slide. And based on this table, you calculate the approximate value for a particular value of lambda and t, and then you substitute directly. Okay. Is it clear? Is it clear? Is it clear to you, everyone? You don't have to solve
Yes,
this
sir.
complicated integral. This is going to be really difficult to solve. Okay. Instead of that, what you have to do is you have to refer a table in the book as well as in this particular slide and find out. So there is a simple example given here to appreciate the concept here. So for example, the fraction of the solar radiation, we have to calculate how much fraction of the solar radiations are present in the visible range. That is what we have to remember. In the last slide, we have said that the most of the solar radiations are concentrated in the visible range and therefore it appears bright. Now we wanted to find out pinpointedly what is the fraction of the solar radiations, total solar radiation, which is between this visible range of wavelength. So visible range of the wavelength is between 0.4 and 0.7. Again, the temperature of the sun we know that is 5780 Kelvin. So we can multiply this 5780 into this lambda 1 and into lambda 2. So that becomes lambda 1 T becomes 0.4 into 5780. So that becomes 2312. Similarly, lambda 2 T becomes 0.7 into 5780. So these two values are 2312 and 4046, and corresponding to these two values we can find out what is the value of F factors. So the F factors corresponding to this first value lambda 1 T, that is 2312. So I can go here, 2312 is in between these two limits. So corresponding value of FB is around 1229 here. If you do the interpolation correctly, that you will get it is 1229. So this 1229 you can put it here, and the second factor is lambda 2T. So that is 4046. So 4046 you can identify here in between here, and corresponding to that value you will get the FB factor. So that is around 4889 by doing the interpolation in between. So whenever such questions are there and the values are not lying exactly on the given values in this particular table, in such cases you have to do the linear interpolation here to find out the values. So these values we have put it in this equation, so we can find out what will be the total fraction of the radiations which are present between this visible light range. So that comes around 0.366. So that means 36% of the total radiation. What it means is 36.6% of the total radiation falls in the range of the visible range of the wavelength between 0.4 to 0.7. Even though the sun radiates the radiation in the wavelength between 0 to infinity, but predominantly that means 36.6% of the radiations are falling in this short range of 0.4 to 0.7. That's it, and that is why sun appears bright. Is it clear to everyone? So this particular thing we have derived here in equation 7. Here you can see the fraction of the radiation between two wavelengths can be directly obtained by using this particular formula. So here you can see this fraction will be given as 1 by sigma integral lambda 1T to lambda 2T and K1 lambda T raised to the power minus 5 divided by exponential of K2 lambda T minus 1 d lambda T. So this can be rearranged in the form of this integral you can represent between 0 to lambda 1T and 0 to lambda 2T, and therefore you will get this directly. So FB lambda 1 lambda 2, FB lambda 1 lambda 2 is given as FB 0 to lambda 2 minus FB 0 to lambda 1. This subtraction of these individual fractions will give you the fraction of the radiations falling between the wavelengths lambda 1 and lambda 2. That's it. Okay, is it clear to everyone? Is it clear to everyone? Can we move to the next slide? Hello?
Yes, sir.
Okay. So now let's look at the Kirchhoff's law. Kirchhoff's law says that the emissivity of the black body, which is in equilibrium with the surrounding, is equal to its activity. That is what the Kirchhoff's law is, that we can derive directly. So rate at which body 1 emits the radiant energy. So that is given as the emissive power into the surface area. So E1 A1, that will be the rate at which the body 1 is going to emit the radiant energy, and rate at which the body 1 is going to receive the radiant energy is going to be what? Absorptivity multiplied by the heat flux into area A1, isn't it? At equilibrium, both these factors should be same, so that is equated. Correct. So this A1 get cancelled out. So we get E1 equals to the emissive power will be given as alpha 1 into Q, isn't it? Now the same equation we can write down for a black body. So for a black body, EB is given as 1 into Q because the absorptivity of the black body is just 1. So EB is equal to just Q. And if we divide both these equations, this equation and the next equation, what we get is E1 by EB is equals to just Q. Isn't sorry. E1 by EB is equals to alpha 1. E1 by EB is equals to alpha 1, and E1 by EB is nothing but what? Emissivity. So that is E1 epsilon 1. So epsilon 1 equals to alpha 1. So what it means is the emissivity of a body which is in thermal equilibrium with its surrounding is equals to its absorptivity. So that is what the Kirchhoff's law is. Okay. So this is the last slide about this particular lecture. We will I will upload the I will load the another PPT. So this was all about the basics of the radiation. Now let's look at slightly more complicated part of the radiation. Let me just present the another one. Okay. Okay, so slides are visible to everyone. Hello.
Yes, sir.
So these new slides are visible. Okay. Now, so far we were, dealing with the simple type of analysis which probably you all have done in your JE days or maybe in the first year physics. Let us look at some more complications in the radiation. Okay. So far we have not looked at, the directional nature of the thermal radiation. So in radiation, the direction of the radiation is also important. How much surface area is facing to another body, that is extremely important. So shape factor, view factor, these are the additional things which are important when we are looking at the real life radiations. Okay. So let us look at some more details along this direction. So consider the radiation emitted from a differential area dA1 towards the area A2. So there is a differential surface area dA1 and it is emitting the radiations. So what we are considering is the radiations emitted from the area A1. These are emitted in all the direction like as shown by a hemisphere here, and only part of that is absorbed, or part of that is incident on A2, isn't it? So that therefore the directional nature of the thermal radiation is very important, isn't it? So what area of dA1 is facing A2, that is very important here. Okay, so let us look at this here in more detail. So radiation streams out in all direction encompassed by a hemisphere. So here you can see the dA1 is radiating the radiation in all the direction encompassed by the hemisphere here, which is shown here. So only part of the radiations, only the part of the total radiation which this dA1 is emitting in this hemispherical region. So only part of the radiation streaming out from dA1 which falls within the solid angle subtended by A2 at dA1 will reach A2. So this is a very important statement. So what we are saying is, even though this dA1 is radiating the radiating in the this hemispherical region, only part of the radiations which falls within the solid angle, which falls within this solid angle, subtended by this surface area A2 at DA1. So what is the solid angle subtended by this A2 at DA1? Only the radiation emitted from that are going to reach to A2. That is what it is saying. Okay. So from this, what we can conclude is the solid angle subtended by this A2 at A1 is important in order to find out how much amount of radiations emitted from this DA1 are actually going to reach to A2. Okay, so the solid angle subtended by area A2 at the differential area DA1 is numerically equal to the area A of the portion of the sphere of unit radius with center at DA1, which is cut out by conical surface with vertex at DA1 passing through a perimeter of A2. So what it means is, so this solid angle can be obtained directly by drawing a hemisphere of unit radius, and that hemisphere will cut somewhere here. So whatever the solid angle, you will get it here. So that is going to be the solid angle subtended by A2 at A1. Okay. So the solid angle subtended by area A2 at a differential area DA1 is numerically equals to the area. So this area which is cut by a unit circle or unit hemisphere around this with the center here at DA1. That is what it means. Okay. Is it clear to all? Yes or no? So this is the area A2. I wanted to find out what will be the solid angle subtended by A2, solid angle subtended by A2 at A1. So how we can find out? We have to draw a hemisphere here with a unit radius, and wherever that hemisphere of unit radius is going to cut this particular cone, that particular surface area is going to give me the solid angle subtended by A2 at DA1. And the center of that another hemisphere which I am going to draw with a unit radius should have a center here at DA1. That's it. Is it clear to everyone? Hello? Yes or no? So this solid angle is measured in a unit steradian and denoted by a symbol omega. Okay. So now let us look at some more detail here. Now consider the case here. The another surface area A2 is of hemispherical shape. So this A2 is hemispherical shape and DA1 is a small block like this, isn't it? Small differential area DA1. Now since this entire DA2 is covering this DA1, so all the radiations emitted from DA1 are so basically will be captured by this A2. So it doesn't matter whether I move this DA1 at any location along this circular plane which is given at the bottom. So still all the radiations emitted by DA1 will be captured by A2, and therefore the solid angle subtended by A2 at DA1 in this case is going to be 2 pi. Okay. Is it clear? So this entire thing will be accounted by the angle, solid angle 2 pi. Okay. So it doesn't matter whether I move this DA1 at this location, anywhere along this circular plane at the bottom. Even though at any position I move this DA1, still my solid angle subtended by A2 at DA1 is going to be 2 pi. Okay. Now let us look at the detailed analysis of this solid angle, how the solid angle is going to affect the radiation. So that part we are accounting in this particular example. So here you can see there is a differential surface area here with a normal n, and there is another area dA. So we wanted to find out the solid angle subtended by this area dA at dA1, isn't it, that we trying to find out. So consider the solid angle subtended by a differential area dA through which the radiation emitted from dA1 passes. So the radiation emitted from dA1 are going to pass through this solid angle subtended by area dA. Here n is the normal, again r is the radius, psi is the zenith angle, and phi is the azimuth angle in a spherical coordinate. So based on the spherical coordinate geometry, we can clearly find out this width is going to be r sin phi d psi, sorry, r sin psi d phi, where this d phi is nothing but this particular angle, and also this width here is going to be r d psi. So d omega subtended, differential solid angle d omega subtended by a differential area dA at the surface area dA1 is given by, so d omega is given as dA by r square, where r is the radius, r is the distance between dA and dA1. So d omega is given as dA by r square. Again here this area dA will be given by what? This width and this length. So this becomes r sin phi d phi into r sin psi d phi into r d psi. So that becomes r square sin psi d psi d phi. And if you divide that by r square, so d omega is given as sin phi d, sorry, sin psi d psi d phi. Okay, this is just from the spherical coordinates directly. Okay. So now what we are interested in? We are interested in finding out the total emissive power. Remember, total emissive power, that is what we are trying to find out when we are accounting the directional nature. So far, remember in the last slides which I have shown, there we were looking at the emissive power of the black body, isn't it? Total emissive power of the black body also we have looked at, but there we have not accounted the directional nature of the thermal radiations. Now we are trying to account the directional nature of the thermal radiations. So so let us look at the another concept here. The another concept is the intensity. So the total intensity of the radiation. So when I am saying the total, this total word, whenever I am using this total word, this total means it is summed over the range of wavelength between 0 and infinity. Okay, so the total intensity of the radiation in a given direction is given as radiant flux passing in the specified direction per unit solid angle. So basically this is defined as the intensity of the radiation, total intensity of the radiation is defined as the emissive power divided by the solid angle. Okay, so IB lambda is nothing but d EB lambda by d omega, where omega is nothing but the solid angle. So the intensity of the radiation is defined as radiant flux. So radiant flux is nothing but what? EB lambda passing in a specified direction per unit solid angle. Per unit solid angle. That means EB lambda by omega gives me the intensity of the radiation. Intensity of the radiation. Okay. So here we are talking about the spectral intensity. This is nothing but the spectral intensity. Why I am saying the spectral intensity? Because this intensity is with respect to a particular lambda. That is why IB lambda, IB is nothing but the intensity of the radiation. IB lambda is nothing but the spectral intensity of the radiation. So spectral intensity of the radiation IB lambda is given as d EB lambda by d omega. D EB lambda by d omega. So differential emissive power, spectral emissive power divided by the differential solid angle, that gives me IB lambda. So EB lambda, now I can directly find out EB lambda by rearranging this equation. So what I get is EB lambda is given as integral IB lambda d omega. So this integral is with respect to the solid angle, isn't it? Again, IB lambda. So remember here d omega is what? D omega we have obtained in the last slide here. D omega is nothing but sin psi d phi. I can put it here. So IB lambda sin psi d phi I have put it here. Okay, again this IB lambda, which is nothing but the spectral intensity or a monochromatic intensity. This spectral intensity can be represented in the form of normal, spectral intensity. So that is the intensity in the normal direction using a Lambert's law. So the Lambert's law is stated here as the IB lambda, which is nothing but the spectral intensity, is given as the INB lambda. So that is nothing but the spectral intensity in a normal direction into cos psi. So this is given by a Lambert's law. So I can put it here. So I can put it in this particular equation. So INB lambda is in a normal direction, is independent of any angle psi, and therefore this is a constant. So INB lambda cos psi sin psi d phi. So here INB lambda and INB lambda is a constant, so that I can take it out, and d phi I can integrate between d phi. Remember, d phi is varying in this particular case. D phi is varying between 2 pi 0 to 2 pi, isn't it? This is going to take a this d phi is going to vary as like this. So that is going to vary between 0 to 2 pi, whereas the psi is going to vary between 0 to pi by 2. So that is what is being put here. So this d phi has the limit between 0 to 2 pi, whereas the psi has the limit between 0 to pi by 2. So I can integrate this d phi between 0 to 2 pi, so that becomes 2 pi directly. So this 2 pi is taken out. So EB lambda, after integrating over the over the solid angle, what we get here is 2 pi INB lambda, and in the integral 0 to pi by 2 cos psi sin psi d psi. And this integral of cos psi sin psi d psi comes out to be 1 by 2. 1 by 2. So what we get is EB lambda is obtained as pi into INB lambda. INB lambda. So what it means, this is a very important relation. So what it gives is, it gives basically the spectral emissive power of a black body. Here B is always, whenever we are putting B is basically black body. So EB lambda is nothing but the spectral emissive power of a black body is pi times the spectral intensity in a normal direction. So this is INB lambda is a spectral intensity in a normal direction. So EB lambda is given as pi INB lambda. Okay. So the spectral emissive power of a black body is pi times the spectral intensity in a normal direction. That is what it means. Okay. So again, so far we have integrated this EB lambda only with respect to the solid angle, and therefore we are calling it as a spectral emissive power or a hemispherical emissive power. Okay. But also we know that the intensity, this wavelength of the radiation varying between 0 to infinity, and if you wanted to find out the total emissive power, then this EB lambda has to be integrated again with respect to the wavelength. So that is what is been done here. So total emissive power of the black body EB can be given as 0 to infinity EB lambda d lambda. So this becomes pi, we can take it out, INB lambda d lambda. So this becomes INB. So EB equals to pi INB. So this is also a very important result. So what we are concluding here is total emissive power of the black body, is pi times total intensity of the black body in a normal direction. That is what we are concluding here. Okay. Okay, so far we have obtained the relationship how the emissive power is related to the intensity. Now let us extend these ideas for the heat exchange between two black surfaces. Two black surfaces we are looking at. Okay, so consider two black surface elements DA1 and DA2 at absolute temperature T1 and T2. So this DA1 and DA2 at absolute temperature T1 and T2. Also, the angle these are making with the normal are, so DA1 is making the angle beta 1 with normal here, and similarly DA1 is making the angle with the normal of DA2 by beta 2. So again, both the surfaces DA1 and DA2 are black surface. So we are looking at the black body, the heat exchange between two black surfaces. Okay. So as we have seen in the last slide that the intensity of the intensity of the black body can be obtained in the in terms of the intensity in the normal direction. So that is In into cos beta 1. So this is nothing but the Lambert's law. Okay. So In can be replaced by In is the intensity in the normal direction can be represented in the form of emissive power. So that becomes EB by pi. EB by pi. So this IB is given as EB by pi cos beta 1, and EB is given as emissive power can be given as sigma into T raised to the power 4 from the Stefan-Boltzmann rule. So that becomes IB is given as sigma T raised to the power 4 by pi cos beta 1. So this is the intensity of radiation IB, intensity of radiation IB emitted by DA1 in the direction of DA2. So what is the intensity of the radiation in the direction of DA2? That we can directly obtain by this relation. IB is given as sigma T raised to the power 4 by pi cos beta 1. Okay. Similarly, in this case, the solid angle dW subtended by DA2 at DA1. So now we have to find out the solid angle subtended by remember here these radiations are emitted by DA1 and how much part of that will be absorbed by DA2, that depends on the solid angle subtended by DA2. Remember, whenever we are looking at the radiation from DA1 which has to be captured by DA2, in that case we are looking at the solid DA2 at DA1, isn't it? So here we are looking at the solid angle subtended by DA2 at DA1. So that is given as DA2 cos beta 2 because that is the
Excuse me, sir.
angle this is making with respect to. Yes, please go ahead.
Yeah, I think the voice is very laggy, sir. I was not able to get.
Is it lagging for everyone? Hello.
Yes, sir.
Yes, sir.
Yes, sir, it is
Yes,
like-
sir.
So please stop me in between. Please stop me in between because that is not coming well in the recording later on, isn't it? Please stop me in between. Okay, now it is clear, or should I need to? Okay, just wait. Let me switch off my video. Is it clear now?
Yes, it's better. Yeah.
Is it better? Okay, so check for 1 or 2 minutes. If it is not better, please stop me in between. Okay. Because I am generally on the slide, so I don't get to know whether I'm audible to everyone or not. Okay. Anyway, so we are trying to find out here is, so this is very important thing. Okay. So there are two surfaces DA1 and DA2. Both are so both surfaces DA1 and DA2 are there, and these are black surfaces. We wanted to find out the heat exchange between these. So DA1, so the angle DA1 makes
Sir, it
with
is not clear.
DA2 still not clear. Voice is not clear.
No, sir. No, sir.
Okay. Let another. Is it clear now? Am I audible now? Hello?
Yes, sir.
Yes, sir.
Better than the previous one?
Yes, sir.
Okay. Whenever the audio is not clear, please stop me there itself. Please don't wait. Otherwise, the quality of the video messes up big time, and that's not good. Yeah. Clear? Okay. So we have been on the slide. So there is a two surfaces DA1 and DA2, and both the surfaces are black. We wanted to find out the heat exchange between these two surfaces. Again, the surface DA1, the normal of surface DA1 making an angle of beta 1 with DA2, and similarly the normal of DA2 making an angle of beta 2 with DA1. Now, in this case, the intensity of the radiation emitted by DA1 in the direction of DA2 can be obtained as, so IB is nothing but the intensity of the radiation. So this can be represented as IN into cos beta 1. So this is nothing but the Lambert's law, isn't it? IN into cos beta 1. So this IN can be replaced by EB by pi, because that is what we have obtained in the last slide, isn't it? Emissive power, total emissive power EB is given as pi times the intensity of the radiation in a normal direction. So that is what we have replaced here. So EB by pi is IN is replaced by EB by pi into cos beta 1, and this EB can be represented using the Stefan-Boltzmann law. So that is sigma into T raised to the power 4. So IB is given as sigma T raised to the power 4 by pi cos beta 1. Again, the solid angle. Now this is what we have seen, the intensity of the radiation, which is captured, intensity of the radiation emitted from DA1 captured by DA2. Now again, what we are interested in finding out, we are interested in finding out the solid angle subtended by DA2 at DA1, because DA2 is capturing the radiation from DA1, isn't it? So we wanted to find out the solid angle subtended by DA2 at DA1, but this DA2, the normal of the DA2 is making an angle of beta 2 with respect to DA1, and therefore the solid angle d omega subtended by DA2 at DA1 will be given as DA2 cos beta 2 divided by L square, where L is nothing but the distance between DA2 and DA1. Okay. Now remember, IB we have obtained solid angle dw. Okay, sorry, d omega. Now remember, the rate at which the radiation emitted by DA1 flowing towards DA2 we can directly obtain by multiplying this intensity multiplied by the solid angle, isn't it? Remember, the solid angle intensity is defined as emissive power per unit solid angle, isn't it? So solid angle, if you multiply it to IB, that is going to give me the radiations emitted by DA1 which are flowing towards DA2. So that is what we have done here. So IB into dW. So that is going to be the emissive power, and multiplied by area. So that is going to become a DA1. So that is going to give me the rate at which the radiation emitted by DA1 flowing towards DA2. Okay. So IB d omega into DA1 is going to give me the rate at which the radiation emitted by DA1 flowing towards DA2. So we can put IB here. IB is just sigma raised to the power T raised to the power 4, sigma into T raised to the power 4 by pi cos beta 1 from equation 5, and d omega, that is obtained as DA2 cos beta 2 by L square, and DA1 as it is. So here we can rearrange this entire equation. So after rearranging this entire equation, what we get is cos beta 1 cos beta 2 DA2 divided by pi L square in the bracket sigma T1 raised to the power 4 DA1. So this gives me the rate at which the radiation emitted by DA1 flowing towards DA2, isn't it? Now in this particular equation, this term which is given in the bracket is represented by another parameter which is nothing but df12. So df12 is nothing but the, in this case f12 is nothing but the view factor, shape factor or a component factor of DA1 with respect to DA2. So here subscript 1 and 2 is important. So when we are saying F12, so that is nothing but the shape factor of DA1 with respect to DA2. Okay. So this is nothing but a fraction of radiant heat flow rate from DA1 which intercepted by DA2. This is nothing but the fraction of the radiant heat flow rate from DA1 which is intercepted by DA2. Okay. So now you can clearly see the origin of this shape factor, view factor or a component factor. You might have used this shape factor or a component factor when you have looked at the radiation in your JE days or maybe in your first year. So origin of this shape factor or a view factor is from this. Okay, clear? So clearly now we can see that the rate of heat transfer, if we consider the directional element into the account, that give rise to another factor which is nothing but the shape factor. This shape factor has to be multiplied to sigma raised to the power t raised to the power 4. Sigma into t raised to the power t1 raised to the power 4. Okay. Is it clear to everyone? The origin of the shape factor? Is it clear? Hello?
Yes, sir.
Okay. Now, so far what in this particular slide what we have done, we have found out the rate at which the radiation emitted by DA1 flowing towards DA2, and in a similar manner we can find out the rate at which radiation emitted by DA2 and which are flowing towards DA1. Remember, in radiation both DA1 and DA2 can emit, isn't it? And some part of that will be intercepted by DA1 and DA2 respectively, isn't it? So now, similar to the previous case, we can find out the rate at which the radiation emitted by DA2 flows in the direction of DA1 and is absorbed by DA1. So that is again given as cos beta 1 cos beta 2 DA1. So instead of here it is DA2, so that becomes DA1 divided by pi L square sigma T2 raised to the power 4 into DA2. So we can represent this as dF21 sigma T2 raised to the power 4 DA2. Here F21 is nothing but the shape factor of DA2 with respect to DA1. Now, what will be the net rate of heat exchange? Net rate of heat exchange is going to be the subtraction between these two quantities which we have found out here by equation number 7 and 6, isn't it? So subtraction of equation number 6 and 7 is going to give me the net rate of heat exchange. So net rate of heat exchange between 1 and 2 is given as dQ12, which is obtained as subtraction of both these factors. So that becomes sigma into cos beta 1 cos beta 2 DA1 DA2 pi L square T1 raised to the power 4 minus T2 raised to the power 4. So this can be represented as dF12 sigma T1 raised to the power 4 minus T2 raised to the power 4 DA1, or this can also be represented in a different form as dF21 sigma T1 raised to the power 4 minus T2 raised to the power 4 DA2. Remember here DA1 and DA2 is both are there. So whether we are expressing this entire equation in terms of area DA1, if we are expressing this entire equation in terms of DA1, then the multiplication factor is dF12. If we are expressing this equation in terms of DA2, then the multiplication factor is dF21, isn't it? So that is what is shown here in equation number 8. So from equation number 8, we can conclude that the shape factors F12, dF12 and dF21, these are related with each other in terms of their areas. So dF12 DA1 is same as dF21 into DA2. So this gives a very important relation that the shape factor of area A1 with respect to 2 and the shape factor of area 2 with respect to with respect to area 1, these are related with respect to their corresponding areas. Okay, so this equation number 9 is very important. In fact, this is one of the property of the shape factors which is extremely important, which we have to look at later. We will look at these properties in more detail as we go ahead. Okay. So again, okay. So this entire analysis so far we have done. Remember, okay, I'm sorry. This entire analysis we have done with respect to the differential surface area dA1, dA2, and that is why we have obtained this differential rate of heat exchange. Also, the shape factors here are given in terms of the differential form, isn't it? For two finite surfaces, dq2, this dq2 has to be integrated, isn't it? Because so far we were looking at the differential surface areas A1 and A2. Now in order to get the finite surfaces, we have to integrate with respect to area 1 and area 2. So that is what has been done here. So this equation dq12 which we have obtained here, this equation has to be integrated with respect to area 1 and area 2. So that is what is been done here. So dq12 is integrated with respect to area 1 and area 2. That gives me q12. So q12 is nothing but integrated over area 1 and area 2 cos beta 1 cos beta 2 dA1 dA2 divided by pi l square, and this entire bracket multiplied by sigma into t1 raised to the power 4 minus t2 raised to the power 4. And this can be represented in the form of shape factor as f12 sigma t1 raised to the power 4 minus t2 raised to the power 4 a1. And again it can be represented in the form of another shape factor, that is f21 sigma into t1 raised to the power 4 minus t2 raised to the power 4 into a2. So here the shape factor f12 is defined as 1 by a1 into this entire bracket. So this entire bracket divided by a1 is going to give me the shape factor f12, and similarly this entire bracket divided by area a2 is give me the shape factor f21. Okay, so that is the simplification done here. So this is nothing but the total rate of heat exchange between the area a1 and a2, and that is given in terms of the shape factor f12 and f21. Okay, again sometimes what happens, one of the area is very small. So whenever one of the area is very small, we don't have to do both these integral, only one integral is required, and that is what is been done here. Suppose area A1 is very small, in that case the integral has to be integration has to be with respect to A2 only. So this equation 10 can be rearranged as shown here as equation number 11, where the integration is performed only with respect to area A2. So Q12 is given as integral with respect to area A2 cos beta 1 cos beta 2 dA2 pi l square, and dA1 is taken out from this bracket. So that is since the area is very small, that becomes just A1. So sigma into t1 raised to the power 4 minus t2 raised to the power 4. So this entire bracket is represented as f12. So this is a simplification done here. Okay, so we stop here unless you have any question to ask, anything to discuss. We will stop. We will continue from this point onward in the next class.
Hello, sir.
Yes, please go ahead.
Sir, I just wanted to confirm, you were saying that you will update the boiling and condensation slides on MS Teams. Sir, has it been done?
I have already uploaded, but I think there are some 1 or 2 small mistakes are there. So I will do it right away. Just
Okay.
After this class you will get it, the updated. Okay. So any more questions? Is it all right? Okay, so again, see, we will have, remember that the tutorials are going to be only on Monday now. So there will not be tutorial on Tuesday. Since the attendance is very low on Tuesday, it is better to conduct directly on Monday. So please attend on Monday. Anyway, the recording of the tutorial are always available, isn't it? Is it all right? Is it
Yes,
all right?
sir, fine.
Okay, so I have again one more thing to discuss. I have gone through all your comments in Moodle. So thank you so much for the overwhelming, response from your side. I will try to accommodate as much possible. in subsequent maybe quizzes or major, or maybe so evaluation strategy, as we have fixed that it is going to be best 2 out of 3, that we will stick to, we will not change that. Okay, other than that we will not have any subjective questions will not be there, that is for sure. Okay, so other than that, all your comments I am going to look at more positively, because these are not implementable. So other than that, all your comments are I will try to accommodate as much possible. Okay, then see you on Monday.